In industrial biotechnology, microorganisms are deployed in closed or relatively open vessels, called bioreactors or fermenters. There are inputs of liquids, and due to the conversions in the broth, also outputs of products and liquids with a different composition than the inputs. We further have gas inflow and outflow and input of energy to secure proper mixing. For this course, we usually assume that the inputs and outputs are constant and we have a steady state within the reactor. This applies to the chemostat mode of operation, in which the state and chemical composition of a bioreactor is kept constant by continuously adding fresh medium and removing unreacted nutrients and products, keeping the reaction volume constant. Important for design, test and improvement of microorganisms and processes is to know how fast things go, or what is the rate of substrate and oxygen conversion, cell growth, product formation, including CO2. Here we have an issue. It is not possible to measure the rates with a sensor. Rather, a rate needs to be calculated from selected measurements. And to do so, we need balances. Let me take the example of a compound balance as applies to a system in the broth. A compound I in a solution is added with a certain rate in kilogram or moles per hour multiplied by the concentrations of the compound in kilograms or moles per kilogram solution. The result is a term with the unit kilogram per hour or moles per hour. The fate of this addition is that some can leave the reactor unchanged but with different rate and concentration. If inputs and outputs are different, then there is accumulation over time, also with the unit kilogram or moles per hour. It is important that we know all key mechanisms acting on the compound, such as reaction, evaporation, absorption, degradation, precipitation, etc. Compound balances need to be set up for all relevant compounds in the system, thus for substrate, product, but also for nitrogen source, oxygen and CO2. This should be done in parallel for all phases, gas, liquid, and if solids are present, also for solids. This then presents the compound balance, as I introduced before. The balances for the gaseous compounds don't have the reaction term because there are no cells in the gas phase, but have an additional term, the transfer between gas and liquid in which the cells are present. We use some other symbols for gases, although the units in terms of the terms in the balance remain the same, kilogram per hour or moles per hour. This Ti term, of course, should also be included in the broth compound balances, but there with the opposite sign. Oxygen disappears from the gas and is taken up by the liquid. And CO2 generally leaves the liquid and enters the gas. Measurements are important, and it is wise to check the quality before doing calculations. It is advised to check conservation principles. An element that is added should be found back in the outlet, albeit in a different molecule. For example, the carbon balance says that the amount of carbon added via the glucose should be found back in either the cells, product or the CO2. If these are different and the carbon balance does not close, there should be unknown mechanisms that act upon the carbons. For example, a byproduct can be formed, or CO2 can precipitate with calcium, or think carefully if you really understand your system. The compound balances are the basis for the process, but to judge the performance of the microorganisms, we need the biomass specific rates, also called Q rates. These biomass specific rates have the unit gram per mole biomass per hour, or moles per mole biomass per hour, and are found by subdividing the process rates R by the total amount of biomass present. The specific growth rate, mu, is also a Q rate. Mu is important because it determines cell behavior. Mu can be controlled in chemostats, and other Q rates are dependent on mu. Cure rates are the only way to judge true cell performance. You can be easily fooled by comparisons of primary measurements, for example titers. And my advice, never judge the performance of cells in any other way than via the cure rates. When doing this, you should take care that you do not trip over so-called banana peels. Assumptions such as the biomass concentration in the vessel equals the concentration in the outflow, and the flow in equals the flow out for both gas and liquids are not always justified and should at least be checked thoroughly. If different, you can easily draw false conclusions and make wrong decisions. In industry or academic research, chemostats are used as research tool, but for high throughput screening, often batch processes are the standard. Also, here it is key to calculate the cure rates from balances, where accumulation equals reaction, and the transfer term should be added for gaseous compounds. It is important to realize that all variables are time dependent and the volume is never constant due to titrations, exchange of oxygen and CO2, and evaporation, and therefore we must use the total amount of compound in moles or kilograms and not their concentrations. Further, in batch processes, mu equals mu max, so the cells are tested under conditions that they grow at the maximum rate, which can be far away from the conditions of manufacturing in industry. There, the cell growth rates are very low or even close to zero. Still, screening in batch processes can be a good pre-work for a selection step to find better strains or explore improved environmental conditions. Beware that it assumes that the dissolved oxygen concentration is not limiting, which is often not true. This is a well-known banana peel when working with shake flasks. Here this unit ends. See you next time when we continue our story.